Revolutionary technologies are emerging that could transform how railways approach track foundation systems and ballast management. Research laboratories across the globe are developing innovations that address fundamental limitations of traditional stone-based systems. These technological advances promise to revolutionize railway maintenance practices, extend infrastructure lifespans, and reduce operational costs. The convergence of materials science, sensor technology, and artificial intelligence creates unprecedented opportunities to reimagine how railways support the enormous loads and stresses of modern train operations. Smart ballast systems incorporate sensors that monitor load distribution, vibration levels, and moisture content in real time to optimize maintenance scheduling. These sensor networks use wireless communication protocols to transmit data continuously from thousands of monitoring points throughout the ballast layer. Each sensor measures multiple parameters, including pressure variations, temperature fluctuations, and water content changes that indicate ballast condition. The monitoring systems detect early warning signs of ballast degradation before problems become visible through conventional inspection methods. Advanced algorithms process the sensor data to identify patterns that predict when specific track sections will require maintenance attention. The sensor technology includes strain gauges embedded within individual ballast stones to measure internal stress distributions. Accelerometers detect vibration patterns that indicate loose ballast or inadequate compaction. Moisture sensors identify drainage problems that could lead to ballast contamination. Temperature sensors monitor freeze-thaw cycles that affect ballast stability in cold climates. The wireless transmission systems operate on low-power protocols that enable sensors to function for years without battery replacement. Polymer-modified ballast uses chemical treatments to improve stone durability and reduce degradation rates, potentially doubling service life. Chemical engineers have developed polymer coatings that penetrate the surface layers of ballast stones and create protective barriers against weathering. These treatments reduce the formation of fine particles that contaminate ballast systems and impair drainage performance. Laboratory testing shows that polymer-treated stones maintain their angular shapes through millions of loading cycles, while untreated stones gradually round and lose their interlocking properties. The polymer modifications also improve resistance to chemical weathering from acid rain and salt exposure in coastal environments. Different polymer formulations target specific degradation mechanisms that affect ballast performance. Silane-based treatments create hydrophobic surfaces that repel water and prevent freeze-thaw damage. Epoxy coatings provide mechanical protection against abrasion and impact forces. Polyurethane modifications enhance flexibility and reduce brittle fracture under dynamic loading. The application process involves vacuum impregnation techniques that ensure uniform polymer distribution throughout the stone structure. Geosynthetic reinforcement systems combine traditional ballast with advanced fabrics and grids that enhance load distribution and reduce settlement. These reinforcement materials use high-strength synthetic fibers woven into precise geometric patterns that optimize force transmission through the ballast layer. The geosynthetic grids interlock with ballast stones to create composite structures with superior mechanical properties compared to unreinforced systems. Installation involves placing reinforcement layers at specific depths within the ballast profile to maximize load spreading benefits. The synthetic materials resist chemical degradation and maintain their properties throughout the design life of the railway infrastructure. Advanced geosynthetic designs incorporate biaxial grids that provide equal strength in perpendicular directions. Triaxial configurations offer enhanced stability for curved track sections where lateral forces are significant. The aperture sizes in these grids are precisely calculated to achieve optimal stone interlocking while allowing proper drainage. Some systems include geotextile separation layers that prevent soil migration into the ballast while maintaining water flow. Artificial intelligence analyzes ballast performance data to predict maintenance needs and optimize replacement strategies across entire railway networks. Machine learning algorithms process vast datasets containing historical maintenance records, traffic loadings, weather patterns, and inspection results to identify factors that influence ballast degradation rates. These predictive models can forecast when specific track sections will require attention with accuracy exceeding 90%. The AI systems continuously learn from new data and refine their predictions as more information becomes available. Railway operators use these predictions to optimize maintenance schedules, allocate resources efficiently, and minimize service disruptions. The AI applications extend beyond simple prediction to optimization of maintenance strategies across complex railway networks. Algorithms consider factors like crew availability, equipment scheduling, material supply chains, and traffic patterns to recommend optimal timing for ballast work. The systems can simulate different maintenance scenarios to identify strategies that minimize total lifecycle costs while maintaining safety standards. 3D printing technology is being explored for creating synthetic ballast with optimized shapes and properties that exceed natural stone performance. Additive manufacturing processes can produce ballast particles with complex internal structures that enhance strength-to-weight ratios and drainage characteristics. The printing materials include high-performance ceramics and polymer composites designed specifically for railway applications. Computer modeling optimizes particle shapes to maximize interlocking properties while maintaining adequate void spaces for drainage. The manufacturing process enables quality control that ensures every particle meets exact specifications, eliminating the variability inherent in natural stone materials. Recycling innovations use advanced separation techniques to recover and reprocess ballast with near-original quality specifications. These systems employ optical sorting, density separation, and chemical cleaning processes to remove contamination and restore ballast properties. Automated maintenance systems could deploy robotic equipment for ballast cleaning and replacement without requiring track closures. These emerging technologies suggest that railway foundations may evolve significantly from current stone-based systems, yet the fundamental engineering principles they address remain constant. Whether through smart sensors, advanced materials, or automated systems, the goal remains the same: creating stable, durable foundations that safely support the massive forces of modern rail transport. The innovations represent evolutionary improvements rather than complete departures from established engineering wisdom that has proven itself over more than a century of railway operations. These technological advances point toward a future where railway foundations become increasingly sophisticated while maintaining their essential purpose. The next time you see those carefully placed stones along railway tracks, you'll understand that you're looking at one of engineering's most elegantly simple yet sophisticated solutions. These billions of precisely engineered stones represent the foundation of a transportation system that moves trillions of dollars in goods and millions of passengers safely every year. The global railway market surpassed 200 billion euros in 2024, highlighting the enormous scale supported by these seemingly ordinary rocks. The hidden complexity behind something so seemingly ordinary reveals how much engineering genius surrounds us in plain sight, waiting to be discovered and appreciated.